talking about influence line. And when we say influence line, we are referring to the analysis of a member when a unit load moves from one end to another. And for this particular one, we'll be considering this member AB having a support that is hinged at end A and with a roller at end B. Now the question is, we want to find the influence line of the reactions A, B, and the internal forces at point I, and moment at point I, shear force at point I of this given simply supported beam. When a unit load moves from A to B, that is, a unit load moves from A to B. Now, actually, if it's normal reaction, we could have just analyzed this one, and then we have the reaction at both ends with respect to this unit load. But because we want to look at the way the member will react as the load moves, as the load travels along this section, so we will be using S to denote the distance covered at every point in time. Now, let's assume that we want to look at the influence line of the reaction at A and B when there's an internal force at this point I here. So the distance from here to here is SI, while the distance from this point to this point B is SI prime, and the full length of the beam is L. So for a random position S of the unit load, we take the summation of moments about point B. Why are we doing that? You know, if we want to get the reaction at A, we take moments about point B, and if we want to get the reaction at B, we take moments about point A. So for this particular one, we want to get the reaction at point A, so we take the moments about point B. So we have summation of moments about point B is equal to the reaction at A multiplied by this distance L minus this point load multiplied by this distance. Now, since this whole length is distance L, this short distance is S, so the distance from here to here is equal to L minus S. That is why we have L minus S here, and we take it to be equal to 0. So from this expression, if we want to do the calculation, we have the following calculation. If we want to, let me just show you the calculation for the reaction at A. So we have it this way: summation of moment about B to be equal to this. So our reaction at point A will give us 1 minus x over L. So from this, we already know this to be our reaction at point A. Likewise, we will take moments about point moment about point A to be equal to 0, so that we'll know our reaction at point B. What this means is that if we want to draw the influence line for the reaction at A, this is the calculation that we're going to use. This is the formula we're going to use. That is, when S equals to 0, we have our reaction at A to be equal to 1. And when as S approaches L, when X equals to L, which is the final span, our reaction at A will be equals to 1 minus 1, which should be 0. So take that into consideration, or just remember that when we get there, we will see the diagram. Let me just proceed. So let's proceed to the next step. We have it. This is the, you can see the direction, you can see the influence line. It is 1 at point A, and it is 0 as it approaches, as S approaches point B. So this is what we're going to have for our influence line for the reaction at point A. So if we proceed to look at what we are going to have at let's say at S, let's say unit load at B, that is when S equals to L. I said our A is 0. When S equals to unit load at A, when S equals to 0, we have it as A equals to 1. And likewise at our midspan, that is when our S equals to L over 2, since our RA equals to 1 minus X over L, this will give us 1 over 2 if you do the calculation. Just putting what's it called? Substituting our X to be equals to 1 over 2, or L over 2 rather. L over 2, L will cancel L, so we're left with 1 minus half, so we'll be left with 1 minus half, which will give us half. That is why our reaction at the midspan of A will be half. So taking that into notice, then we'll go to the we're going to how to draw our influence line for reaction at point B. So drawing the influence line for reaction at point B, the same principle that we use will take our moment about point, we turn our moment about point A, then we do the reaction. Now if we do that, we have B times L minus 1 times S will give us 0, which will give us B equals to S all over L. Now influence line for the reaction at B equals to S over L. So and the same thing will follow the same origin for S, that is S moving from this side to this side. So when our S equals to 0, and likewise when S equals to L, we'll look at the reaction. So this is the breakdown of the calculation. We have it this way. So for simplicity, I believe this is clear enough. Summation moment about A, then we have it. We have our S over L for the reaction at point B. So having done that, we proceed to draw our influence line for reaction at B. Mind you, since we have S to be cos RB to be S over L, so we can always look at it when we put our S value to be equal to 0, we have our RB to be equal to 0. That is, at this point, if you are drawing the influence line for point B, at this end A, when our S is 0, our reaction at B will be equal to 0. And likewise, as it moves to the point when X equals to L at this point, then if you put L here, we'll have it as 1. So what this means is that the influence line for reaction at B moves in this direction. So we have 1 at this end here. So let me just show you how it will look like. So this is what we are going to have for influence line for our influence line for reaction at B. So now let's proceed to what we'll have next, which is okay, likewise if we put it at S equals to at midspan, when our S equals to L over 2, we are still going to get reaction at B to be equals to half. So let's proceed to draw the bending moment and the shear force for these particular cases when our at point I, when we have a unit load, a moving unit load at distance S from support A. Now note that we have two cases when our unit load is located between A and I, that is when we have our unit load at this range, and likewise when we have our unit load at this other end. So for both cases, we're going to make a cut at point I. For both cases, a cut at point I will be considered. That is, when we make a when we make a cut here, we have it as when it's loaded at this point, and likewise when it is loaded at this point. So let's proceed. We're going to have this. Okay, I think I should. Let me make it a little bit simpler. Let me make it a little bit simpler. So we have it this way. Since we know that our reaction at A to be equals to 1 minus X over L, and reaction at B to be X over L. So if we have a cut, we have it for this section and this segment. Now when it is loaded at this when it's loaded at this point, and when it's loaded at this point. Now let us look at it this way, that reaction at A, when we take the shear force, this is the reaction at A. This minus this will give us 0 if we want to take into consideration our equilibrium, and when we sum our forces at our S point, summation of our forces along S axis to be equal to 0. Sorry, when our forces along Y axis to be equal to 0. Now, if we look at it, summation of this one minus this is pointing down, this is pointing up. Please take note, when we have it pointing down here, we have it pointing upward here, and likewise the same way we treat it. Now, if we have our reaction at A to be equal to Qi, definitely our Qi, that is our shear force at this point, is equal to 1 minus x over L, which is just the same thing as the reaction we are going to have here. So, and likewise, we look at it for this other one, since we said it's Q. This will be summation of these two will give us 0. So definitely our reaction at B will be equal to minus Qi. So if we have it as since our RB equals to S over L, our Qi will be equal to minus x over L. So let's proceed. Now let's see how our influence line would be for this particular shear force. Normally you are supposed to have something like this. That is, if you consider this reaction at A when S equals to 0 and when when S equals to 0 and when S equals to L. For this taking into consideration the what's it called, this particular diagram, we are going to have something like this for this particular one. At S equals to 0, our Q, if you put S equals to 0, our Qi will be equals to 1, and if you put our X to be equals to L, our Qi will be equals to 0. That is, at S equals to 0 and at S equals to L. This is the normal thing we are supposed to have. This is the normal diagram we are supposed to have for the influence line diagram for this particular reaction at A for this particular case. Now, let us now look at it, and for the reaction at B, what we are going to have. Now, you can see that for reaction at B, at X equals to 0 and S equals to L, our X equals to 0. If S equals to 0, then our Qi will be equals to 0, and at S equals to L, our Qi equals to minus 1. So we are having something like this for this particular influence line for the reaction at others at the concentration of the other side of other member of the beam. So how do we treat such? We try to combine the two diagrams together. Now, if we combine the two diagrams together, this is what we're going to have. We'll have this particular diagram. Now, the point of application of our load is this place. So when we put it into consideration, what we are going to do is that is what we observe from this is that the influence line we are going to consider, if it's loaded at this point, or if we are considering this member A, we take this portion of the influence line, and if we are considering the portion B, we take this other side of the influence line. So if we combine that, we are going to have this particular diagram for what we are going to consider. We have this place. So this is the region, this is our influence line for this one will be around here. So considering this other side, when we load here, when we make a cut, when we load here, we consider this side, and when we load here, we consider this other side, this other side section of the diagram. So this is what we're going to have. So we are going to have this. We have this for the member A and this for the member B. So we consider the two diagrams, we're going to have this, as I've explained earlier on. Now, the gradient for this particular portion of this diagram follows our 1 minus x over L, and the gradient for this follows our minus x over L. So as S moves from A to B, this is what is going to follow. Now, mind you, if we are considering this, then our distance is from xi to L, which is denoted with xi is less than or equals to S, which is less than or equals to L. And likewise, our from this place to this place, from A to the point of application of our point load, is going to give us, let's say, we are going to have it denoted with 0 is less than or equals to S, which is less than or equals to xi. So as S moves from A to B, this is what we're going to follow. So now what it means is that if a unit load is applied at this particular end here, this is what we're going to consider. At this point, we have either this or this. So depending on the area we're considering, when we load it here, we consider this side. When we load it here, we consider this side. So I would like to just explain the influence line for the bending moment before I proceed with an example for clarity purpose. So for the bending moment, we have, having established the fact that our reaction at A is this, and reaction at B is X over L. So a cut at section I gives us these two members, member A and member B. So if member A is from X, and let me say the distance is this SI is the distance, and then member B is distance, it will be L minus XI, since the whole span is L. So what we are going to have is for side A and side B, I want us to see what we are going to have here. For side A, if we take the moment about point I to be equal to 0, we have our mi minus reaction at A times this distance times xi will give us 0. So our moment about I will give us average times xi, which is the same thing as the reaction at A times distance si. Now looking at the other side, at side B, considering this side, now if we turn our moment about I to be equal to 0, we have our moment about I to be equal to moment about I minus reaction at B times this distance, L minus Si, that's the distance from here to here, and equals to 0. So our moment about I will give us this particular solution. Now, you know our R reaction at B is S over L, so this is why we have S over L here. So it's very easy, it's straightforward. Now if we expand this if we expand this, let's say our SL divided by L will give us X alone. You know, this one we can see this for this particular one, but for the other one we have SXI over L. So looking at these two expressions, likewise if we break this down, you are going to have SI minus XSI over L. Multiply this and this, you have this. Now looking at the two expressions, you can see that we have this to be almost the same thing. So what it means is that at point I, we're going to have the same let's say almost the same reaction. When SXI over when we look at our reaction at let's say our moment diagram at point I, is going to give us the same value at the mid span. Now looking at this, we can always try to see what we are going to have for our reaction, maybe when our S equals to 0 or when our S equals to XI, and that is another calculation that I would need to just explain or put down for us for clarity's sake. Now if we look at it, if I put S to be equal to 0 for this particular one, I have XI, and if I put S to be equal to 0 for this, what am I going to have? I have 0. So this one will be almost unsolvable. So that is why we take this side for this, we take this side of the moment diagram to draw this, and this side to draw this particular one. So let me just do the calculation and let me just show you what we are going to have. So we have it this way. At S equals to 0, we consider member B, and at S equals to L, we consider member A. And that is at S equals to 0 to XI, we consider member B, and at S equals to SI to L, we consider the member A section. Taking note that this is the member A section and this is the member B section, the MI that is gotten from member B. Now, using this formula we're going to use this formula when our S is from XI to L, and we're going to use this one when our S is from 0 to L. So if we do that, let's consider this at Si is less than or equals to S, which is less than or equals to L. Now using this member A formula, putting our at the maximum point when our S will be equal to Si, we are going to have this. Just substituting Si into this, we are going to have Si into L minus Si. And using member B, using member B, we have member B, we have this equals to this when we substitute our S equals to Si. Now, the same formula, we are having the same value. What it means is that at the midspan, when our S equals to Si, and it's our the starting point of this and the end point of this, we are having the same formula. I don't know, maybe that is clear enough, but if it's not clear enough, let me still make it a little bit simpler. Again, let us consider it this way. Let us take using only this one. Only this this is the area I want to concentrate on. We have our Si, which is less than or equals to S, which is less than or equals to L. So we are using member A for this. Now when our L minus, that is the maximum point for this particular one, that is when our S equals to Xi, that's our let's say that's the point when our, if you are looking at it, is maybe when our starting point of the member, is L minus Si. That starting point is maybe 0.0 to the other hand L. So at 0.0 of this, when we have this, if we look at it again, this is our reaction at A, as we already know, times Si to give us at the moment at point I. Now at the center point, this S is going to be Si, that is the distance traveled at the center point. Now when our S equals to Si, when our S equals to Si, we are going to have it, this expression, putting our S, changing it to Si, we're going to have it this way, and expand Xi times this one Si, this one multiplying this, we have Si times this will give us Si over L. Now if we expand the bracket, we taking Si out, we have 1 minus Xi over L, and simplifying further, we have taken L as the LCM of the two. We have L minus Si having this. Now from here we can as well say take Si over L out, then we have this. Now looking at this formula, it's this is, let's say this is equation 1, and that is with respect to our moment when we are considering reaction at A. Now let us look at it when we consider reaction at B. That is when if we consider moments with respect to member B, that is we already know that moment at member B is from L to Xi. That is the starting point of member B is L minus Si, and the end will be something like around L. Now the starting point of L minus Si, if we substitute this into the formula, maybe putting our reaction at B, X over L, multiplying by this distance, which is at the starting point. The starting point is the midpoint of reaction at A. Now if you look at this equation 1 and equation 2, you can see that they are similar. What it means is that at the midpoint, this is the midpoint for the two. When S equals to when we have this, we're going to have this as the diagram for our bending moment at the midpoint, where let me say the termination point of point A and the starting point of point B. So let's put that into diagram and see what we are going to have. Let's see what we are going to have, and what we are going to do is that if we are considering just understanding the principle of where your xi is starting from, or when you're looking at member B and when you're looking at member A, we can look at it in the diagram. We're going to have, let's continue with the main diagram. So this particular distance here is where our SI over L multiplied by L minus SI, the equation 1 and equation 2 that I told you about, this is where it's going to meet. Now, having that expression, that SI over L multiplied by L minus SI, using it for our calculation of our moments when we are putting a real life situation, as we are going to show in the next example. Now, looking at this example, we have a member A to B, and we have the loaded in this format. Point load at point 2 meters from the NA, 4 meters from NA, and 7 meters from NA. Now, the influence line that we drew the other time, this is the influence line for reaction at A, as we already know. Now, we are asked to estimate the reaction at A and the internal forces MI, QI for the given influence line. Now, if you can recall, the other time I told us that the reaction at the moment at the midpoint is what's called, that is xi over L into L minus Si. Let me just bring that in. I told us this. Now, if we have this, now, how did we come about this 2.4 here? Using this equation, our xi is from here to here, which is 4. So if we substitute 4 into that, we have 4 over our L is this total span, which is 10. 4 over 10 times, now L minus xi, which is 10 minus 4, that's 6. Now 4 times 6 divided by 10, that is 24 over 10, which is 2.4. That is why we have 2.4 here. I think it's clear enough. I think that is a little bit clear enough now. So we have it. This is the calculation 2.4. Now, please note, if this is 2.4, what we're going to do is we're going to distribute the whole this 2.4. It varies as it diminishes to 0 here. We are going to calculate the height for this particular place, and likewise the height for this particular place. Now, what we have here at midspan, so definitely at midspan, if from here to here is 24 at 4 meter length, definitely at 2 meter length is going to be half of this. That's why we have 1.2. And likewise, if we consider this other span too, from here to here is 6, and at 6 meter length we have 2.4. Then at 3 meter length we have half of this, which is 1.2. So this is where we arrive at this particular value. Now let's go to if you can recall the shear force diagram the other time. Let me quickly get that for us. So for the shear force, we have this formula, 1 minus S over L, and likewise minus X over L. And if you can recall, you were told that if we are considering this side of the shear force, you take into consideration the member B, and if you are considering this side, you take into consideration the member A. Why are we doing that? If you look at the shear force, we have a value of 0.4 here and a value of 0.6 here. So which one is for the 0.6 and which one is for the 0.4? So if we are treating the one at this member B, then we consider this value for this, and member A, we consider it for this value. So let us look at what we are going to have using the formula I just showed us just now. So we have minus X over L, which we are going to use for this value, which we are going to use to get this value here. So our S, what's our distance S, is 4, so minus 4 all over 10, that's 0.4, so definitely 0.4, and that's why we have the negative here. This is the value we have here. And if we want to consider the other one here, we're going to use 1 minus x over L. Our x is 4 and our L is 10. 4 divided by 10 will give us 0.4. 1 minus 0.4 will give us 0.6. That is why we have 0.6 here. So I think that is clear enough. And having arrived at that, what we are going to do now is we are going to just substitute, use this particular value to multiply whatever we have here for our reaction at A. And since we have 3-point load, that means we are going to, for the reaction at A, we are going to multiply this times this plus this times this plus this times this. That will give us the total reaction at A. And for the moment, depending on where we are considering, all we just need to do is we multiply this by the, if this is the one that you're taking into consideration, you just multiply this by this, and if it is this alone, you multiply this by this, and etc, etc. Since we are asked to consider the moment at I, definitely we consider we sum everything for this particular. We are taking the effect of all these forces into consideration. We will multiply every one of them with their respective moments, which we have this times this plus this times this plus this times this. So let's proceed and see what we have for the reaction at A. As I've explained, we said 20 times 0.8 plus 30 times 0.6 plus 40 times 0.3, giving us this. And for the moment at I, we have 20 times 1.2 plus 30 times 2.4 plus 40 times 1.2, giving us 144. So that is the moment at point I that we are considering. Now let us look at it this way. The value for the reaction force at A when the unit load is located at point C is 0.8. That is, the value of the reaction force at this point is 0.8. If only the point load of 20 kilonewton at C was applied to the structure, usage of the effluent will give us the following value for the reaction. That is to just be this times this. If it's only this point C, 20 kilonewton force that is being applied. So I think I've explained that. And likewise, if it's only point load of 30 kilonewton at point D, we just apply the 30 times 0.6, then we have the value. So let us look at the one that is interesting that I want us to look at is the this particular shear force diagram on. Now the shear force diagram, we have 2 points. We have one of 0.4, we have one of 0.6. So depending on where we are considering, we'll have this one. If we are considering for the what's it called, this is point load acting at this point, definitely it's having that first value and second value. So we just look at it this way. We consider the left hand side and the right hand side. For the left hand side, we are taking this left hand side, that is, if we are taking the left hand side, then the value is 0.6. If we are taking the right hand side, the value is 0.4. So we have it at this one, 20 times 0.2 plus this times 0.6 plus 40 times 0.3. Mind you, look at I want us to look at the sign, because this is positive here. You can see that it's positive. And if you observe this one at the right hand side, we'll consider the right hand side, this and this, minus, we're having minus for the 30 because it is this is at the negative side here. That is why we're having this for this. Why are we using 0.4 here and 0.6 here? As I told you earlier on, that when we're considering this side of the member, we take into consideration this member, and when we're looking at the loading on this side, we consider this member. So that is why we are having this. So we have 26 and minus 4. So we are taking the higher one, which is this. We are using it. We use the highest for the sign, which is this. We are using that. What we're going to use for our design. I believe that is clear enough. And if there's any further question, please kindly drop in the comment section so that I can respond to your question. And if it's clear, you can just give a thumb up. Thank you very much. The next one will be coming up very soon, will be on uniformly distributed load, which I will explain in my next YouTube video. Thanks and have a lovely day.